All right, so today's video is going to be about timing considerations in Helix, and this is going to be how to set up a federate to execute at the times you want and return the granted times that are desired for any particular federate. When we came up with the design requirements of Helix, one of the design requirements was to have Helix be scalable out to a rather large number of federates, potentially 100,000 or more different federates. To do this, we kind of looked at how controllers would work and the implications of a central controller versus a distributed. And a central controller would represent a bottleneck, and that includes controlling time advancement. So that made it difficult to go that route and led us down the path of distributed timing. And this leads to the requirement that time advancement must be controlled in a distributed fashion and done locally for each federate. And the design of Helix, that leads into kind of a hierarchical design. So that also implies the interprocess communication must be coordinated and distributed and hierarchical. And so that kind of led us down the path of what the timing system in Helix must look like. And so the extreme of that is that every federate has independent time control and is responsible for making its own, making sure its own federation is consistent and executes correctly. And that allows each individual federate to customize and tune the timing requirements that it needs, independent of all the other federates in the system. So we want to do this to allow parameters and time controls to be updated on the fly. So sometimes the timing requirements change in different federations. So you start off with one and then you go to a different mode and you need finer timing control. This also prevents the controlling values for the time. They don't need to be transmitted to other federates, and other federates don't need to be aware of the timing requirements on each individual federate, and gives us quite a bit of flexibility in federate integration. So you can add in federates that don't impact others much or control the time very well in the simulation. So the way it works is you have an incoming message. This can be a value or message of some kind. And there's a property called an input delay to this. And this is controlling how much time elapses between when the message is scheduled to arrive and when the federate can actually see it. And on the other side, there's an output delay. So federates may send a message, and it takes a little bit to propagate to the outside world before other federates can be able to see it. These can be set to 0, but one of the use cases of these is for parallel execution, because you know that if a federate can't send another message in a certain window, it can execute in parallel with others. And with small federations, this probably isn't that important, but when we get rather large numbers, these values will determine kind of look ahead and parallel execution timing of the federation. The other properties involve kind of periodicity of how often a federate may return time. So one of those is called the period, and an offset is closely related to that. So basically this states that a federate may only grant times at integer values of the period shifted by an offset value. So in this case, n times the period plus the offset, and you see kind of how a timeline of this may look. And external events, they basically do not show up to the federate until the time is granted. So if you sent one at t0 plus half of the period, it wouldn't show up at the federate until the next granted time. This can be modified by the time delta, and basically the time delta is a limit on how closely spaced two granted intervals may be. So you can see how that impacts this. So if you specify a time delta in a period, you can kind of figure out which periods are allowed and which are not, and it'll only grant at specific periods. The minimum time delta on the clock is 1 nanosecond, so that's kind of the minimum default time resolution. The helix code itself can be recompiled to go faster if for some reason there's a need to, but it defaults to 1 nanosecond. And the time delta interacts closely with the period, and they can, if you don't use the offset, they're effectively interchangeable, but they have different meanings. As stated previously, there's kind of 5 properties that can be controlled: the input delay, output delay, period, offset, and time delta. And these can be set dynamically as a federate is running. There's some restrictions on how fast they change internally because to prevent non-causality, but in general they can be set dynamically. There's also a number of flags that can control the time in Helix. There's 2 flags that must be set before initialization: observer and source only, and these are indicators that the federate either does not publish any data and it just receives data, or it is only a data generator and nothing's expected to be sent to it. If something were to be sent or received by an observer or source only, that is possible inside Helix, but it represents non-deterministic behavior. There's also a number of flags that can be changed at any time during the simulation. The uninterruptible flag is an indicator that only the time requested should be returned. Ordinarily, Helix can return a time earlier than what is requested if updated values or messages are available. So the uninterruptible flag will prevent any interruptions from occurring. The only update on change and only transmit on change are basically change detection. This change detection does not have a limit value. It's basically a binary equivalence, but it's an indicator that if values should only be updated if they represent a change, or they should only be transmitted if they represent a change. And then the last flag, wait for current time updates, basically indicates that a federate should wait until all other federates have passed the requested time. And this can be useful if you know one federate is dependent on others and you want to get those values at the current time, but it's requesting, but it has to update. So ordinarily, if multiple federates will request a time at the same time, they will be granted execution in parallel, and the wait for current time updates will prevent one of the federates from doing that. There's a dependency chain detection here, because if you specify multiple federates that are dependent on each other with this flag, that could represent a blocking situation, so that will not be allowed inside Helix. And you'll get a warning message and other errors if you try. The time control in Helix is done by the request time function, and this is a blocking function. So it will block until the time can be granted. There's an iterative time call, and if you tune into the next tutorial, you'll get some more details on the iterative controls in Helix. This is also a blocking call, but the iterative time will return a time and a convergent state, which is a enumeration of iterations, whether there was an error, a halting situation, whether it's iterating, or the time has advanced. There's also async and complete versions for non-blocking alternatives of these function calls. And with that brief tutorial, if anybody has any questions on the time control in Helix, please feel free.
Hi Phil. This is Chiu-Hua from PNL. While using the time request, I noticed, at least for the Java binding sign, the return is an array. It means it could be multiple, granted time. So why is this kind of design? Is any special consideration for this?
It is that probably depends on which version of the Java bindings you're using. If you're using a really recent one, if you're using Helix will only return a single value. It's probably something we need to look at in the Swig bindings of how that gets tied in.
Okay. Yeah, I just saw maybe there was some underlying special condition, like maybe return a couple of granted time.
No, it should only return one time value.
Okay, gotcha. Thank you.
All right. Well, thank you, Phil.
All right.